We are back once again. This is Daily LeetCode, day 60. Yes, Daily LeetCode, day 60, Daily LeetCode. Reflections on yesterday. We did a lot of reading yesterday. I think it was quite a large amount of reading. The ADM, the Holy Text, right? The Algorithm Design Manual. And then we switched up, we changed, right? We switched up, we changed. So we started doing coin change. We got beat down by coin change. Ended up with quite a crazy solution, which now I'm realizing is very, very interesting, right? I was reading our boy Thomas's comments. This man is a goated commenter. Goated commenter. I read all this earlier, like 5 minutes ago. The legendary explanation. Basically, right, Thomas is just saying, because I was drawing it yesterday, but I was getting lost in the sauce, right? We were visualizing coin change as a graph problem. And so there are multiple ways to get to 11, right? But the shortest way, so we consider doing a BFS, right? Bottom up, right? So if we start at 0 and count, or we start at the lowest denomination coin and then count up to amount, there was a lot of different paths to check, but I was getting lost in the sauce because if you do, I was funny because during the problem yesterday, I was like, oh, if I start at our target instead of our source, right, maybe it would be better, but I got lost in the sauce and I figured it would actually be the same, but it wouldn't be the same because the BFS, right, the first time we reach 0, it's actually going to be our lowest level, which is really interesting. That's pretty much what Thomas is mentioning here, that oftentimes, right, you can, if you swap the target and the source, right, so I was starting from the source and searching for target, but if you start from target and search for source, is it faster? And yeah, Thomas, goated comments here, just basically goated comments, right? So, legendary comment. You are goated. Yeah, next time we run into this problem, we can definitely dunk on it because we wrote a BFS solution bottom up and it got TLE, but we should just write it top down. But yeah, it's just interesting. The next time I do, which is going to be 3 days from now, we're going to draw it, right? So we know that we can do it, right? So that would be pretty cool. But yeah, legendary comment, man, legendary comment. I actually read this and I was like, duh. But that's how I be sometimes, right? But I'm actually a bit short on time, right? About 10:30 on a Saturday morning. And we have some things to do later today. So I actually have to be somewhere by 12, but we have 45 minutes on the clock anyway. So it is what it is. It must be done. The grind cannot stop, right? So usually I try to do a breakdown of reading and problem solving. And so today I think I'm just gonna have to break up the time, right? I can do 15 minutes of reading, right? And then I'll do 30 minutes of problems. We have some cards due today that we want to get done. So we'll do 15 minutes reading, right? And then 30 minutes doing some problems, right? And we just try to get a little bit better every day, but the gains on reading is just too great. So just finding more ways to formulate these problems is too strong. So a necessary evil, but I would say, yeah, yesterday's video was called Coin Change. What did we call it? Coin change is unstoppable. Coin change is very stoppable. So that is a good thing, right? Thanks to our dear friend Thomas. But other reflections, evaluate division is an impossible problem, right? Every time I look at this problem, every time I mention I'm going to try this problem on recording, I never get to it. This is probably subconsciously what's happening, because I'm just not seeing how you solve this problem with a disjoint set. That being the case, or union find, that being the case, this is besides the point. We're going to try it again, and then if we can't figure it out I think I'll try it one last time tomorrow. Otherwise, we're just going to read the solution, right? Because there's a way that they're formulating this problem. I think it's also probably a mental block where I think I can't solve it. So it kind of feels futile to try. And I think the mind is often like kind of like a general purpose machine, right? And I feel like sometimes you really have to believe you can solve it. Otherwise, your engine's running at like 20%. So I feel like this problem is unsolvable. So my effort that I'm giving the problem, right? Basically, I'm saying I feel like if this problem is a maze, I feel like I'll never get out of the maze. So I'm not really trying to get out of the maze. But it's possible, right? Sometimes to get out of the maze, you just need to feel like you can. So that's what it is. That being the case, we're going to jump into it. But before we jump into it, right, I'm actually thinking maybe a new form. Maybe we'll stream this. Maybe we'll stream our LeetCode grinding a few times a week. I think I'll start with one time, right? Maybe the time that I'll aim for is like, maybe I'll aim for like a weekday or something, maybe 7 or 8 one time a week could be cool. That way we could all grind at the same time, right? So I think that would be pretty cool if everyone was doing LeetCode problems at the same time, maybe the same problems. I'm pretty sure there's also already a platform for that. But that being the case, maybe we'll start streaming some LeetCode problems, but it'll probably be on YouTube, to be honest. So it is what it is. That being the case, it is 45. That being the case, shout out to the people who have joined the channel recently. Shout out to Thomas, Control Copy Ninja, I'm Just That Guy, and anyone else who drops in to just drop a like or watch the video, right? Appreciate you. And if you're not in the Discord, you're gonna want to join the Discord because we're giving out. There's probably gonna be something. Like 2 weeks ago we had Drake in the Discord, right? So I think this week or maybe next week we're gonna try and get Elon maybe to come through to the Discord. This is actually true. Yeah, this is actually true. We had a live concert by Drake in the Discord earlier last week. So, I mean, that's why we have I think we have like 300 to 400 million people in Discord right now. So you're going to want to join. It's very hype, very interesting, and very hard to get into, very exclusive. So that being said, we have 45 minutes on the clock. And I think the goal today is to read for 15 minutes, and then I'll try again on Evaluate Division. So I'm going to start the timer now, but when I unpause the recording, maybe I just record myself reading. That's kind of weird though. So that's kind of weird, I think. So I don't know if I'm going to do that. But I'm going to start the timer, and then I'm going to probably pause the recording. I don't know. Is that weird? If I record myself reading, is that weird? That's kind of weird. So I'm going to part the timer. When it gets to 30, I'm going to unpause, right? And then, I'm going to unpause. And then, we'll just jump into Evaluate Division. So that being the case, I'm going to start the timer and then pause. So we are back. Just finished a little bit on the ADM, but yeah, very interesting. I'm still working on the BFS chapter. It's interesting because a lot of what is being said in this chapter has a lot to do with coin change in a weird way, because we realize that at BFS top down, it's actually faster than bottom up, which is interesting. So I'm noticing that BFS in terms of shortest path problems is just a cheat code. And I always usually do a DFS, which means I visit the entire graph. So even with another problem like snakes and ladders, I'm realizing top down would have been faster as well. Yeah, top down would have been faster. So that's interesting. But that being said, there was also an interesting implementation. Maybe I'm reading through right now. It's interesting implementation because I usually do it a different way, right? I usually use just a queue for level order traversal or BFS, but they were using like two Boolean arrays for discovered and processed. But it's interesting because intuitively I understand what they're mentioning, because when I write a BFS algorithm, right, there are different things you can do, right, depending on if you're processing the vertex early, right, in the middle of the process, or at the end, right? And what they're pretty much showing with this chapter is that, right, if you want to be more specific, or you can actually use like specific spots, right, where you can actually know, right, pretty much insert special logic. So it's just interesting to see. So yeah, that being said, right, we have about 28 minutes remaining, right, before I do evaluate division. Fortunately, the cards come first, which I just realized. So we're gonna try and blow through these cards today. Pretty much revision on some of these cards, but we have twosome here, right, and we'll just jump into a lot of these implementations. So, right, given an array of integers nums and an integer target, return the indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution. So that's a pretty big part, right? You may not use the same element twice, right? Because they want two distinct indices to add up to target. You can return the answer in any order, right? So given a nums array, right, and our target 9, right, find the two indices, right, that sum up to target 9. Since we're returning indices, right, we can't sort our input since this would destroy it. And another way we could, right, but we have to pretty much, there's a version of this we can do with n log n, because we'd have to sort, right, and then we could run an algorithm that would also run in linear time to find the targets that sum up to 9, right? But then additionally, we'd have to have some sort of map before we sort it, right, so that we can map the numbers that we find to the indices. That would be n log n with linear space as well, right? But I think there's another version that you could do with linear time. There's probably another version you could do with linear time and linear space, right? So I think it's just a better solution if we go with the faster one, right? We'll use less time, and n is better than n log n. So I think the linear time solution, right? What if we iterated through the array, right? Let's look at it from a process driven approach. For if we iterated through the array, right, we know that we're searching for our complement number, right? And what does that mean, right? So we have 2, right, and our target is 9. The number that would give us the sum, right, of 9, right, 2 plus what equals 7, right? So to get that, we can just say, right, our target is equal to our num. I mean our complement is equal to our target minus our number, right? Our target is 9, right, and the current number we're at is 2. That means our complement is equal to 7, right? But we need pretty much a way to tell if 7 exists in the map, 7 exists in the array, right, in constant time. To do that, right, we're going to need a map, right, which is going to have up to n elements within it, right? But we'll notice, right, as we're iterating through the array, if we check if our complement exists in this map, right, it doesn't, right, because we're at 2. So what we could do is beforehand, right, we can just iterate through the array, right, and we can create a map, right, of number, so 2 to index, right? Then we'd have 7 to 1, right, 11 to 2, and so on, right? And then we could iterate through the array again and just check if the complement exists. But I actually think it's simpler to combine them, right? Because two numbers have to sum up to give us a particular value, and addition, I think addition is commutative, right? We actually don't have to worry about missing our target once. So what I mean by that is that 7 plus 2 is the same as 2 plus 7. So when we go to 2, right, we're going to check if 2 is in the map at this point, right? Because we're going to combine the map creation and the linear iteration of the array to this in just linear time, right? 2 is not in the map, right? So if it's not in the map, we're going to add it to the map. So we're going to have 2 is equal to index of 0, right? Now it's actually 2 plus 7, right? So we missed our chance, right? But fortunately, 7 plus 2 also equals 9. So we'll do, hey, what's our complement, right, when our number is 7? It's going to be 9 minus 7, which gives us 2. And since 9 minus 7 gives us 2, right, we can check if 2 is in the map. It is, so we can return our current index, right, and the value, right, for the key in the map, which is going to be the index. So our approach can look something like this, right? Now I'll comment this part out. Equal a new map, right, with number to number, right? And then we're going to iterate through our array, right? And from here, right, we're going to need our num, right? And our number is going to be nums sub I. Additionally, we're going to need our complement, right? And our target is going to be our complement is going to be target minus num, right? And then we're going to want to know, right, if the map, right, has a value for our complement, right, then we want to return our current indice because they want a tuple. And can we do it in any order? Only one valid answer exists, which is important. Right, we also know there's always at least 2 numbers in nums because there's always at least one solution. You can return the answer in any order, which works perfectly. So we can return I, and we're going to need the index for our complement, which is going to be the value for the complement. So we can return that. Otherwise, right, we can just add it to the map. Right? Now I'm thinking we don't need this else case. We can just do map.set num, right, equal to this index, right? And we actually don't have to return anything. We'll return -1, but we know there's always one solution, so we don't have to return anything. But we know that we need, just to appease TypeScript, we should probably return something. So let's see if that makes sense. We'll have 2, right? Our number is 2. Our target is going to be 9. Our complement is going to be 9 minus 2, which is 7. Does the map have 7? It doesn't, right? So we add, right? We create an entry in the map of 2 to the index 0. Then we get 7, right? We calculate our complement. 9 minus 7 equals 2. Does our map have an element of 2? It does, so return I, and getting the index of that complement, which is going to be 0, right, plus our current index, which is going to be 1. So we know it works there. Does it work for this? 3, 2, 4, and 6, right? The complement for 3, right, is going to be 6. I mean, the complement, right, for 6 and 3 is going to be 3, right? But fortunately, we check if it has a complement first, right, and we know that it doesn't, right? So this example is essentially checking, right, that we're using 2 separate elements because 3 plus 3 does equal 6. Right? But fortunately, we can't consider our current element as an element in the map, right? Because we don't add it until afterwards. So we actually need a second 3. But basically, we're going to say 6 minus 3. Does 3 exist in the map? It doesn't. So we add 3, create an entry in the map, mapping index 3 to the number 3 to the index 0. Then we go to 2, right? Is 6 minus 2, which is 4 in the map? No. Right? So we set the number 2, right, equal to the index 1. Then we go to target equals 6, right? And right, we know that 2 plus 4, right, and 4 plus 2 both equal 6. Now is our second chance. So we do 6 minus 4 equals 2. Is 2 in the map? It is, so we return that value. So I think we should be good. This would run in linear time with linear space, since for any arbitrarily large array, right, our map could have up to n keys, right, and we're going to iterate over the entire array. All right, so now we have best time to buy and sell stock. They're given an array prices where prices sub I is the price of a given stock on the ith day. right? You want to maximize your profit by choosing a single day to buy one stock and choosing a different day in the future to sell that stock. So return the maximum profit you can achieve from this transaction. If you cannot achieve any profit, return 0, right? So this is an interesting problem. Let's map our problem statement to our example. So you have an array prices where prices of I is the price of a given stock on the ith day. We want to maximize our profit, choosing a single day to buy one stock and choosing a different day in the future to sell that stock, right? So we know that return the maximum profit you can achieve from this transaction. So we know that you can't sell on this, you have to sell on a day in the future. So you can't buy on day 1, on day 2, right, and sell it on day 7, right? I'll give you a profit of 6. Best you can do is buy on day 2 and sell on day 6 or day 5, day 6, and get a profit of 5. It's 5 because our buy-in was 1 and our profit is going to be our sell price minus our buy-in. So 6 minus 1 is equal to 5. So I think what we can do is just basically we'll have 2 competing priorities, and the goal will be to minimize our buy-in, right, while maximizing our profit. So I think this could be accomplished, right, if we just have 2 variables. We have profit, right, which is going to be equal to negative infinity. This is because we want to maximize our profit, right? And since we're going to be doing that, we want to value that if we ever take the max of our initial profit and our potential profit, we always get the value that's not infinity, and then profit getting down the line, it'll allow us to have a value that is always at minimum 0. Then we'll have our lowest buy-in, which is going to equal prices sub 0. Now, does prices sub 0 always have a minimum element within it? It does. So if that's the case, we can say our profit, yeah, that's the worst. We'll say our profit is equal to prices sub 0, right? That way, at the end, we'll return profit, but additionally, we're going to iterate right through each price of prices. And at each moment, right, even when the elements in the array is 1, right, we're going to say our lowest buy-in is going to be the math.min of our lowest buy-in currently, right, and the current price. And our best profit, right, is going to be the math.max of profit, right, and basically our current either profit, right, or the current price, right, minus our lowest buy-in. And I think that makes sense, but let's check. Iterating over prices, right? Profit is 7, right? And our lowest buy-in is also 7. On our first iteration, our lowest buy-in is going to be 7. Our profit's going to be 0, right? Right. So now I'm realizing we actually don't want our profit to be prices sub 0. We want it to be negative infinity, like we said, right? That way we take the max. It'll either be price minus lowest buy-in, which is going to be 7 minus 7, which is 0, or negative infinity. Right, then our lowest buy-in is going to be 7. Then we're going to go down the line. So our best profit is going to be 6, right, minus our lowest buy-in, which is 1, which equals 5. So this would run in linear time with constant space. Dropping rainwater. When was the last time I did this one? 7:30. That was a while ago, almost 14 days ago. So given n, this is a DP problem, but given n non-negative integers, actually, what if we save this one? If we save this one for tomorrow, I think we can actually do some DP. We could do some DP. Yeah, I think we can do a little bit more deep. Like, I want to spend more time on this one in terms of how we do the DP, maybe explore it from a different angle, because I know the solution that I use. I want to try a more natively DP solution. So we'll actually do convert. We don't have enough time to explore trapping rainwater like I'd like to, so we'll save that one. We'll say, given an integer array nums where the elements are sorted in ascending order, we have an integer array nums, elements are sorted in ascending order, converted to a height balanced by BST. A height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. Interesting. So let's map this to our problem statement. We're given this array here. It's already sorted, right? And if we're going to convert it to a height balanced binary tree, if we're going to turn it into a BST, it already has to be sorted, right, in ascending order. So that's going to be helpful. And then we can say a height balanced binary tree is a binary tree in which the depth, the two subtrees of every node, never differs by more than 1. So there is one thing we do know. We know that in order, right? We know that in order traversal, right, of BST equals ascending order array, right? We know that that is true already. So if we know that that is true, right, then we know that one of the core issues of the problem is already solved for us. The array is already sorted, right? So what that means is what we need is a method of layering, basically creating a binary tree. Basically, we can reframe the problem as convert. I think that's what the problem is called, right? Convert sorted array to binary search tree. But I think what we also want to reframe it to is convert array to binary tree. Right, and to do that, I think what we're going to want to do, right, since it's sorted, and for every BST, right, elements to the left of a node have to be less than the current element in the node, or the parent node, and for a given node, right, like 0, all the elements in its left subtree have to be less than it, right, and every element in the right subtree has to be greater than it. This has to be true for every single node. So even for -3, that's true. Right, and empty nodes don't count. For 9, 9 is less than 5, but greater than 0, which is important. Right, and I think what we're also seeing with this problem, right, is that in order traversal of the BST is not unique, right, and I think that means it depends, right, if it's left leaning or right leaning, right, because in the event that you have two elements, right, let's say you have an element like this, right, or an array like this, see an array like this, right, it's unknown or unknown which element, right, should be taken as the goal node here. So you can either take 4, right, or 5. So I think we can see that in this example here, right, where we can either have 9 be a child of 9 be a parent of 5, or we can have 5, right, 9 be a child of 5. So 5 can be a child of 9, or 9 can be a child of 5. Same thing here, right? So it depends on which node you take as the parent node. That being the case, I think there's a way that we can work this out to make sense. I think we want basically a recursive. We want to be able to work with a recursive range over the array, right, and build into tree, right? And to start, I think to start that in general, we're going to need we're going to have to do a recursive function, right? So when I say a range, right, we're going to need a range over the array, right? Because when we start, we're going to need a root node, right? We know the root node is basically going to be the length of the array over 2. This array is length 5 over 2 is 2.5 floor is 2, which means that the parent is going to be 0. So we can get a root node. Now let's say we have a range, right? Now let's say we want to set -3, right? equal to this recursive function again. So we have a new range, right? -10 to -3, right? And we do, right, 2 over 1. Yeah, we have 2 elements, right? Over 2 gives us 1, right? Even if you floor it, right, you get 1. So we're going to get -3, right? So we're going to say our left subtree equal to -3. Then we'll do another range, right? So we'll go left, right? And that range is just going to be, right, range of 1. 1 over 2 is going to be 0.5. Floored is 0. Our left subtree is going to get set to -10. So I think we can make this work with the recursive range over the array, right? And then the element or the node, the recursive function, right, is going to have to return a node, right? And if that's the case, then we can just return the node it creates. So I think if that's what we want, I think we can create a function called convert, right, and return. And we're going to pass in nums. Our start range is going to be the 0th element, nums.length -1, which is the last range. And do we need one more variable? I don't think so. I think we do, though. I guess we'll continue for now, but I think we do. I think we need a way to propagate the node. Right, I think we do need one. So we'll say tree node, right? Right, so I think we need a way to propagate everything. We're going to say new tree node, right? And convert is going to have nums, which is an array of numbers, right? Start, which is a number, right? And it might be more easy if we say left, which is a number, right, which is a number, right? And the node, which is a tree node, right? We're going to return a tree node for null. Now, a good question is, can our BST be empty? No, because we're going to have at least one node, right? So how do we know that we can even create a node? To know that we can even create a node, right, we need to know that left is still less than right. Right? If left is less than or right, then are we still in business? Right? I think we might need an equals sign. Let's say we have one element, right? 4. Our left is going to be 0, right? And our right would be 1. We could do, if we calculate our center, right, it would be 0 plus 1 minus 0 over 2. Right, we 0.5 floored to be 0, right? So this is fine, I think. Yeah, this is fine. So left is less than right. We're in business, right? We can calculate our pivot, our center, which is going to be left plus the math dot floor of right minus left over 2, right? And we're going to say, right, that the node we created right, so this is where we get into the thing. I'm thinking now, like, let's just run with it for now. Let's just say we know that we created the node variable. Let's just say we propagate it. We're not propagate, we're just going to ignore it for now. We're going to shadow it technically for now, but I think we can make this make sense. We'll have node. We create a new node, right? We're going to set its left and right subtrees equal to this recursive function. It means we have to return the node, which is fine, actually, right? Because, okay, the setting is going to be done, or the assignment is going to be done, right, in the parent node's assignment. Basically, what I'm saying is the convert function returns a node, right, and we're going to do node.left equals convert, which means that the subtree is going to be assigned by the parent node. So create a new node, we'll say new tree node, right, with nums subcenter as our number, right? But now we want to set this left subtree, right, equal to this function again, but with a new range. So we're going to pass in nums, right, with left, but our right is going to shrink, right? So what's our left range? If we look at this array here, right, we're going to create a new node with 0 as our head, right, our root, which means the next range we want to consider for our BST is going to be -10 and -3, which means that left is going to stay the same. We're actually going to do right -1, right? Then we can copy this and say node.right is going to be equal to, so if we're at 0, right, our right node, right, our right range is actually going to be, left is now actually going to be center, oh, not right -1, that's my bad, center -1. Our right portion is going to be center +1, right, going to right, which is going to be the end of the array, right? And at the end, we're going to want to return node, right? And if left is less than right, we're going to want to return null. So I think this makes sense, but let's see if it makes sense. I have 0, right? We convert nums, right? We're going to call convert with the range of 0 going to, that's the length of this array, 5 minus 1. It's going to be 0 to 4, right? 0 is less than 4, right? So 0 plus 4 minus 0 is 4 over 2 is 2. Our center is going to be 2, 0, 1, 2. Our 0, 1, 2 index is going to be 0. We create a new node with 0 at our top, right? And then we call convert with num sub left and center -1, which is 1. So our new range is 0, 1, -10, and -3. So is 0 less than 1? Yes. Let's create a new center, right? 0 plus 1 minus 0, which is 0 over 2 is 0.5, floor is 0, right? So we're actually going to take -10, right? Since we're taking -10, we're going to create a new node, right? And so now we're going to have a new node, right? So the tree we're actually building is this one. We're going to have -10. Then we're going to set -10 equal to the node.left of left, which is 0, and center, which is 0 minus 1. So now we go into convert again, but 0 is not less than -1, so we return null for this. So our left is going to be null. We're going to do right, so nums, right, going to center plus 1. Center was 0, right? So we're going to have 1, and right at the time is also 1, right? So we're actually going to have to set this equal to left is less than or equal to right. Then we go into convert, right? Left is going to be 1 and right's going to be 1, which means we're still in business. Calculate our pivot or our center. It's going to be 1 plus 1 minus 1 is 0 over 2 is 0 plus 1 is 0. Node is going to be 1th index, going to be -3. The left and right for both of these are not going to make sense because left is equal to 1 and our right is going to be 1 minus 1. 1's not going to be less than 0, returns null, right? And then here we're going to say is 1 is 2 less than 1. No, we're going to return null. So we're going to return the node, right? Then we're going to pop back up to 10, right? And we're going to set, right, 3 equal to node.right. Then we're going to return the node, pop back up to 0, right? And all of this is going to get set to node.left. Then we're going to do the right subtree. So I think this makes sense. Let's try it. So that's pretty cool. And I think what I'm also remembering is that, right, whether we're left leaning or right leaning is actually going to depend on seal here, floor or seal. So if we floor our center or if we seal our center is going to depend on how, it's going to create our left or right leaning tree. And additionally, we're going to want this equal sign to make sure that we consider subsections of the array where we only have one element. So the time complexity of this, I'm thinking would actually be the height of the tree. I think the time complexity would actually be the height of the tree, right? Because we go down here and we have a new range. Now we visit every element in the array though. we visit every element in the array. I think what's special is that the space we use is actually the height of the tree. I think it would be linear time, but the space we use would actually be the height of the tree. No, the space is because the tree is height balanced. That does make sense. All right, it's height balanced, which means we only go so far. Does that mean that for an array of size n, that the height of a tree is log n? That's a good question. So we'll pause, we'll stop there, but I have to jet. But day 60, that's a wrap.